So when we looked at this population growth example with insects being preyed upon by birds, we solved the differential equation. So here's the differential equation we got. And when we solved it, we got this function down here. So the population is 5,246 plus c times e to the 0.009531 times t. And what I want to do now is just have a look at what this all looks like on the slope field so that we can get some understanding of like why exactly is it that this 5,246 shows up. It might seem a bit odd that there's this constant here. So let's put this all on a graph. So I have entered this constant k here. The slope field looks like this. Okay, notice the labels on the axes, so I've had to zoom out quite a bit to make the changing slopes on the slope field visible. Okay, for our constant c, right, we can make it anything we want here. For now, let's set it to 0, I guess. And the solution is right here. So this is where c is 0. And right, our formula for our solution down here, if c is 0, then you just get the constant solution 5,246, which looks like this. And if we make c bigger, then the population sort of takes off exponentially. And if we make c negative, then the population crashes. So let's think about why that makes sense. Remember, what's happening here is we have a population that's being preyed on by birds. So and the birds are eating 50 individuals a day. So for the population to survive long term, what we need is enough population growth to overcome that 50 individuals per day that are being eaten by birds. So if the population starts out big enough, so remember what really controls C is the initial condition. If the population starts big enough, then the population growth can overcome that 50 individuals per day that are being eaten, and the population will grow. And once the population grows a little bit, then the population growth accelerates because there's more and more excess population growth beyond those being preyed upon. So it makes sense that if the initial condition is large, if the initial population is large enough, then it continues to take off like this. On the other hand, if the initial population is small enough, like any smaller than this 5,246 value, if the population starts out any smaller, then there isn't enough normal population growth to make up for the fact that 50 individuals a day are being eaten. So there are, say, 45 or 40 new individuals per day, but 50 are being eaten, and so, there's a net loss in population. And once that process starts, of course, if you lose a few individuals on net, on the next day, you're starting out with even fewer, and so you're going to lose more individuals. And so you get this sort of exponential crash in population. Of course, GeoGebra just understands this as a formula that I've typed in. So GeoGebra graphs this as if the population can go negative, but of course when the population hits 0, it stops and stays at 0 from then on. So this constant term really is just the equilibrium population where the normal population growth exactly makes up for the 50 individuals that are being eaten by the birds.